Okay, let's dive into this. Imagine you've got a small patch of ground, right? Maybe just a square meter,
Tiny space.
and you want to grow something, say, tomatoes. You want
Yeah.
the absolute most tomatoes you can get from just that little area.
The classic backyard problem. How many
Yeah,
plants do you actually stick in there?
exactly. It
Yeah.
sounds simple, but, well, it's tricky. Too few plants, you're definitely not making the most of the space.
Right, wasted potential.
But if you cram too many in, they end up fighting each other, don't they, for light, water,
Yeah,
nutrients?
they compete like crazy. And
Yeah.
ironically, you can end up with less total harvest because none of them thrive.
So how do you find the exact number, that, sweet spot for the best yield?
It's a perfect example of an optimization challenge, finding the maximum output per area. And the source we're looking at today, it tackles this head on
Okay.
and uses a pretty powerful mathematical tool to get a solid answer.
And that tool, let me guess, is differentiation
Yeah.
from calculus.
You got it. Differentiation. Might sound a bit theoretical, maybe intimidating to some,
Yeah, definitely sounds like high-level math.
but this source shows how it applies directly, like really practically, using differentiation to figure out the exact planting density to get the biggest harvest from that square meter.
Okay, walk me through that. How does it work?
So the source basically looks at the relationship between how many plants you put in that square meter, that's your density, and the total amount of, say, tomatoes you get out.
Right, density versus yield.
And it's not just a straight line. Initially, you add more plants, your total yield goes up. Makes sense, more plants producing.
Uh-huh.
But as the source points out, eventually that competition factor kicks in harder. The rate of increasing your total yield slows down. It hits a peak.
And then if you push it further with even more plants,
The total yield can actually start to drop because the individual plants are just too stressed, too crowded. They don't produce well.
so you can actually model this relationship mathematically, like create a function. Yield depends on density.
Precisely. The source works with essentially a yield function and differentiation. That's the key to finding the highest point on the graph of that function.
How so?
Well, the derivative of that function tells you the rate of change. How quickly is the yield changing as you slightly increase or decrease the planting density?
Okay, right. The slope of the curve at any given point.
Exactly. So if that derivative is positive, adding another plant still gives you more total yield. You're climbing up the curve.
Makes sense. Keep adding plants.
But if the derivative is negative, you've gone past the peak. Adding more plants now actually hurts your total yield. Competition is winning.
Ah, okay. So the sweet spot,
The sweet spot, as the source highlights, and this is fundamental calculus optimization, is where that rate of change is zero, right? Where it switches from positive to negative.
where the curve flattens out at the very top.
That's it. Find the density where the derivative equals zero, and bam, according to the model and the source, that's your optimal planting density, maximum yield per square meter.
That's pretty cool. Taking an abstract math concept and using it to solve such a, well, down-to-earth problem like gardening efficiently.
It really shows that calculus isn't just symbols on a page.
No, it's a tool.
Practical tool for finding the best way, the most efficient way when things interact like this. Planting is just a really clear example the source uses.
Okay, let's wrap this up then. So this deep dive, looking at our source, really showed how differentiation lets us pinpoint that ideal planting density.
Yep, the exact point to maximize your yield per square meter.
It just underlines how calculus can be a powerful, practical problem solver for optimization in the real world, not just theory.
It's about getting beyond guesswork or just trial and error, using analysis to find the genuine optimum.
Right. Which really makes you wonder, doesn't it? How many other situations in everyday life involve finding a maximum, or a minimum for that matter?
Maximizing efficiency, maybe profit in a small business, minimizing waste.
Maximizing performance. Could these things also be tuned using, similar calculus ideas?
It's likely. There could be hidden optimizations all around us, just waiting for the right mathematical tool.
Something to think about next time you're trying to make the most of anything, really.